Welcome back to this lesson. The title is called the Arithmetic Series. This is part 1, and we have a part 2 with additional problems to follow on with this guy right here. So up until this point, we've concentrated on what is the concept of a series in general. It's when you add up terms. And we've also concentrated on the sigma notation with the big Greek letter sigma. That's how we write down when we add up a sum of terms. So that's in general how we're going to represent all of these, what we call series, when we add up a bunch of things. Now we've also talked about a few special, very special series in passing. We've talked about the arithmetic series and we talked about the geometric series. But we have never actually added up the terms of the arithmetic series. And we've never actually added up the terms of the geometric series. So that's what we're going to concentrate on here. We're going to go back and revisit the arithmetic series. We're going to write down the terms, we're going to talk about it, and we're going to actually figure out an equation or a formula to add up the terms of an arithmetic series. And I'm going to prove that this equation works. I'm going to do a proof to show you how it works. We're going to apply it to some problems. And in a few lessons, we'll do the exact same thing for the geometric series. So at the end of these guys, you should understand what arithmetic series is, what a geometric series is, how to find their sum without actually grabbing a calculator and adding the terms up. We want to be able to, for instance, you might have 1,000 terms in your series. You want to be able to find the sum without actually adding up all of those numbers in the calculator. So that's what we're going to be doing here. And this kind of thing goes on and used in algebra and trig and calculus and beyond. So it's something that you're going to see over and over again. So we want to talk about the concept of an arithmetic series. So let's go back and let's pick a very simple one so that we can talk about something concrete. Let's talk about the arithmetic series that looks like this. 2 plus 4 plus 6 plus 8 plus ... plus 100. Now, how do you know this is an arithmetic series? Because arithmetic sequences, which are just the listing of the numbers, they always differ by a constant, by a number that we just add to each of the terms to get the next term in the sequence, or in the series in this case. So here we're adding 2, then we're adding 2, then we're adding 2, and so on, and you go all the way up to your final term being a 100. So because we know this, then we know that this is arithmetic. Arithmetic. And it has to be true for all of the terms. Every term you must be able to get by adding a number to the previous term. But what we want to do is figure out what is the sum of this arithmetic series. Now, obviously, I could grab a calculator and go 2 plus 4 plus 6 plus 8 plus 10 plus 12, blah, 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 all the way till I get to 100. It's going to be a big number, and I'm going to be pressing plus a bunch of times. We don't want to do that. We want to figure out what is an equation that will let me calculate the sum without actually adding up all of those terms. So in order to understand how to do that, we need to talk about, I need to introduce a term. And this term that we're going to talk about is very simple. It's called the partial sum. So let's look at this series. This is term number 1, term number 2, 3, 4, and so on and so on. And then we have, eventually we're going to have 50 terms when you really look at it all, because 2, 4, 6, 8, 10, and then all the way to 100 is actually going to be 50 terms in this series. So we have the concept of a partial sum, right? What is a partial sum? We use the letter S to denote, that's a kind of weird looking S, sorry about that, but we use the letter S to denote partial sum. So if I'm going to talk about the partial sum of the first 2 terms, I put a number 2 under the S. That means I just want to add up the first 2 terms. So what is this going to be? It's going to be 2 plus 4. I know that you can add that up and you'll get 6. I don't care about calculating the sum now. I just want you to know that when I put an S with a 2 underneath, it just means add the first 2 terms of the series together. Okay? If I put S with a little 3 under it, it's 2 plus 4 plus 6. This is the partial sum of the first 3 terms of this arithmetic series. And you might guess that the S sub 4 is 2 plus 4 plus 6 plus 8. Okay, the first 4 terms of this arithmetic series. So this is the concept of a partial sum. So why am I writing down partial sums? Because now we want to generalize the partial sum to a general equation. What I'm going to do here is I'm just going to write down the answer. I'm going to write down what the sum of any arithmetic series is. Right? Then we're going to do one quick little problem, and then I'm going to prove it to you with a formal proof to show you why this equation I'm going to write on the board actually works, because I want you to know where things come from. All right? And then we'll work some more problems at the end. So these are the partial sums. First 2 terms, then the first 3 terms, then the first 4 terms, and then we have what we call, in general, the sum of any arithmetic, not just this one, but any arithmetic series. And that sum is the following. Instead of first 2 terms, first 3 terms, first 4 terms, it'll be the first n terms. However many terms I want to add together is going to be equal to n multiplied by the first term plus the last term that I care to have in my addition divided by 2. So this is what you will see in any textbook in algebra, pre-calculus, calculus, things like this. Okay, so what it's telling you is, if I want to figure out, for instance, the first four, the partial sum of the first 4 terms, I would put a 4 in here. Then the equation would be 4 multiplied by the first term, 2, plus the last term, t sub 4, because remember I put 4 in here, the 4th term, which is 8. I would add those together, multiply by n, which is 4, and then I would divide by 2. So this allows me to use this arithmetic series formula to find the sum of any arithmetic series I want. For instance, in this one here, I have a lot more than 4 terms. It goes all the way to 100, but I'm skipping by 2, so there's actually 50 terms there. So for that, I would put 50 in here, 50 in here. I'd have the first and last terms, and then I would divide by 2. Now, before we go off and actually do it, I want you to kind of understand what this equation really means. So I'm going to write it again. We're going to say S sub n for the n number, the nth partial sum is the way you would say this, is equal to n. Instead of writing it like this, I'm going to write it like this. N multiplied by a fraction, which will be t1 plus tn, the first and the last term, divided by 2. All I've done is kind of break it up so it's not written like this and pull the n out, multiplied by this guy right here. What is this term? What is it? What is that term? This term is the average value of all terms. All terms in the series that I'm considering, because I'm trying to only add up to the nth term. So if I take the first term plus the nth term, the last one that I'm considering, and I divide by 2, then this is just the average value of those terms, right? And then of course I'm multiplying by n terms. And I'm hoping that you can see by breaking it out like this and talking about what this equation for the sum of the arithmetic series is really doing. Okay, what's going on is when you're adding up terms, you have a first term, and then you have a next term, next term, next term, and then you have some last term over here. But the arithmetic series, every term just differs by adding a number, adding a number, adding a number. So if I take the first and last terms, add them together, divide by 2, I'm going to get the average value. I'm going to get the value right in the middle of all of those terms, right? And by using that average value and multiplying by how many terms I have, I can arrive at the exact value of the sum. That's what it's basically doing. I want to illustrate a little bit more why it works over here. I think I want to do it on the next board over here. So let's revisit our series here. Let's say we have 2 plus 4 plus 6 plus 8 plus ... plus 100. I want to add these up. It's not 100 terms because I'm skip counting, right? So it's actually 50 terms. So what I'm going to write down is the fact that what this arithmetic series here is, it's 50 terms. 50 terms. And also the first term is equal to 2, right? And the 50th term, when you go ahead and count through it, the 50th term is 100. That's the last term in the series that I'm considering, right? And I want to figure out what is the partial sum of the first 50 terms. See, this is the partial sum of the first 2 terms, the partial sum of the first 3 terms, the partial sum of the first 4 terms. I want to find the partial sum of, or the sum of all 50 of them. So according to this equation, the way it's going to work is you're going to come down here and say, well, it's n times t1 plus the first and last terms divided by 2. So I have how many terms? I have 50, right? And then I have the first term is 2, the last term is 50. I'm sorry, not the last term is 50. The last term is 100. 100. And it's divided by 2, right? So what do I get here? When I do this, S50, it's going to be 50 multiply, what is this? 102 divided by 2 is going to give you 51. Okay, what is this 51? This 51 is the average value of all terms. In other words, I have so many terms here I can't really write them all out. But imagine I wrote them all out in a line. Then somewhere right in the middle, literally in the middle of all of those terms, would be the number 51. That represents the average value of all the terms. Now, I want to find the sum of all of these terms. Some of these terms are smaller than the average, like all of these are smaller than 51. But an equal amount of them are going to be bigger than 51, going all the way to 100. So even though some of these terms are smaller, and so when I add them up, it's smaller than this average number, but there's an equal number of terms that are bigger than 51 that are too big. So it all balances out so that if I just take this and multiply by the number of terms I have, even though some of the terms are smaller and some of the terms are larger on average, by taking the average value, multiplying by the terms, I'm getting the actual sum. And it's always going to work out that way, and the only reason it works is because arithmetic series with arithmetic sequence numbers, they're all evenly spaced like that, right? Everything's evenly spaced. So by finding an average value in the middle and knowing how many terms I have and multiplying, I'm going to get the actual sum of everything. Again, some of the terms will be too small and contribute less to the sum, but the terms on the other side of this number are going to be too big and they'll overcompensate toward the sum. It'll all balance out so that the actual sum is going to exactly equal what this is, to what this is. So when you do this in a calculator, the sum of all 50 of those terms is going to be 2,550. And that's the number that you would get if you literally sat down and in the calculator did 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14 plus 16 all the way up till plus 100. All right? So this is essentially how we're going to use this equation. We're going to use the arithmetic sequence equation, the arithmetic series equation, to calculate the sum without actually adding up all the terms. But you might ask yourself, why does it work? Now, I've tried to kind of explain by using averages, give you an actual feel for why it works. Like in your mind, the whole argument I've just done hopefully has helped you. But we still want to do a proof. Even if you don't totally understand the proof or just kind of get the basic idea, it's still a really good idea for you to watch it because it gives you a feel for how things are proved in math. In math, all I care about is figuring out what the equation is for the partial sum, the nth partial sum. I can do anything legal that is possible to do to get there. So what we're going to do is we're going to write a generic series down. In other words, I picked numbers to make it easy to understand, but we're going to write down a general series, and then we're going to play around with it, and you'll see how at the end of the day we're going to get this equation straight out of the proof. So let's go ahead and do that over here on the other board. Right? First thing I want to do is I want to write down the series 2 times. And the first time I'm going to write it down the regular way, and then I'm going to kind of walk you through what we're going to do after that. So the nth partial sum is going to be a bunch of terms that we're going to add together. What are those terms going to be? It's going to be the first term, that's always t sub 1. Plus, this is an arithmetic series. So every term just differs from the previous term by adding a number. That number we call the common difference, d. In this series, the common difference was 2. We add 2, we add 2, we add 2, so the common difference was 2. So for this second term in this generic series, it's just going to be t1 plus 2. I'm sorry, not t1 plus 2, because it's a general. We're trying to keep it general. It's going to be t1 plus d. d is just a common difference. In our example before, d was 2. Okay? What would be the next term after this? Well, what I would do is I would add d again, so ultimately it would be t1 plus 2 times d. Think about it, because if you go here, this is plus d is 2 in this case. This is plus 2 again. So to go from here to here, I'm just adding 4. So to go from here to here, I'm just starting with the first term and adding 2 times the common difference. So I can keep going down this way, but ultimately I'm going to put a dot, 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 and I'm going to start toward the end. Okay? The very last term of the series is going to be t sub n. That's the very last term. The first term is t1. The very last term is tn. What term comes right before t sub n? Well, it's going to be t sub n minus d. Right? Think about it. If the last term, if you go back to our numbers, if the last term was 100, then the term right before it is 100 minus 2, which is 98. So all I'm doing is I'm saying the last term is t sub n, and the one right before it is t sub n minus d. So let me clean things up a little bit, and I'm just going to put a few more dots. This is really all I want to write down. So I'm writing down the series in math speak. I don't want to put numbers. I want to keep everything general. I have a first term. The next term is just adding 1 common difference. The next term is adding 2 common differences. And then I get all the way to the end. I'm going to have a final term. And then the term before that will be the final term minus that common difference. And then there's terms all in between. All right? So far, we haven't proved anything, but we just wrote a series down. Now, again, I told you, you can do anything you want in math as long as it's legal, and we want to try to recover that equation. So here's how we're going to proceed. We're going to write the exact same series down again underneath it, except we're going to reverse the order of all the terms. Because if I add the terms up this way, it's exactly the same sum as if I start here and I add them in reverse. Just like 2 plus 3 is 5, and then 3 plus 2 is 5, no matter how I do the operation in the addition, I'm going to get exactly the same number. So this sum can be written a second way. I'm going to call it, I want to use a different color, I think I do. This is still Sn. I'm going to get the same answer, but I'm going to go in reverse. So let me start at the end and say the final term is t sub n. Okay? What is the next term going this direction? It's this one. So it's going to be t sub n minus d, like this. And then if I were to continue going backwards again, what would be the term right before this? It would be tn minus 2d. Just like there's a plus, here's a minus. So it's going to be t sub n minus 2d, like this. So starting from the end, it's minus d and then minus d again. And then I'm going to put some dots, like this. And then we're going to go to the other side. What is the end? The end point is t sub 1. So I'm going to put t sub 1 over here. What would be the term right to the right of that guy? Because remember, I'm writing my sum going this way. So the last term is here. The one right before that is this one. So t1 plus d. You might say, why is he doing this? I haven't explained why I'm doing it yet. But what I'm telling you is I can write the sum of the terms as the sum of all of these terms in the arithmetic series. And then I can write the sum of the terms a second time, simply just reversing the order and going and adding the terms in this direction so that the last term is t1 and the first term is tn. That's all I've done here. And then what I'm going to do is I'm going to draw a line under all of these, right? And I'm going to add them together. How can I add them together? Because remember, any equation with an equal sign, if I have two equations, I can add the left-hand side and I can add the right-hand side together. Just like a system of equations. You can solve a system by addition. Add the left, add the right. You may not understand why we're doing it yet, but you certainly know that it is legal to do that. Because this is just an equation. And so is this one. Don't let the dots fool you. Those are just terms in the middle. It's perfectly fine to add these together. So what am I going to get? Sn plus Sn is going to be 2 times Sn, because I'm adding them together. There's two of them. When I add these terms together, what am I going to get? I'm going to get T1 plus Tn, adding this term to this term. What's going to happen when I add these together? Okay, it's going to be T1 plus d plus T1 minus d. But you see, if I were to add these together, the d and the minus d would disappear. That's why I actually flipped it around, to make the d's disappear. So I'm still going to have these added together. I'm going to have T1 plus Tn for the second term here. What happens if I add these together? Same thing. The 2d and the negative 2d will go away, but these will still be added together. So I will still have a T1 plus Tn, like this. And then we skip over to the end. What's going to happen here? The d's are going to cancel, but I'm still going to have these. I'm going to have T1 plus Tn. And then these guys are going to be added together. I'm going to have it's Tn plus 1. I'm going to write it as T1 plus Tn to match everything else. So all I've done is added the left-hand side, and it turns out that when I add the right-hand side together, all of the d's cancel, and every single term is exactly the same. Every term is the same. And how many of those terms do I have? I mean, think about it. I have 1, 2, 3, 4, 5, all the way up to n. There's n terms here. So when I add them together, how many of these little parentheses am I going to have? I'm going to have n terms on the right-hand side, and they're all the same. So what does that mean? That means on the left-hand side, I'm going to have 2 times s sub n. On the right-hand side, there's n of these things. So it's going to be n times what's inside, T1 plus Tn. These terms are identical, but there's n of them. So I'm multiplying by n. Finally, I want to solve for the sum. S sub n is going to be n times T1 plus Tn divided by 2. And if I remember correctly, that's exactly what we have right here. The sum of the arithmetic series is always the sum of the first term and the last term divided by 2 multiplied by n. Now, you might look at this and you might follow this, but you may say to yourself, I would never in a million years figure that out on my own. Great, I'm glad you feel that way. I wouldn't have figured it out on my own either. I didn't wake up in the morning one day and say, I'm going to prove how arithmetic series are added together. I didn't do that. But what happens is people figure these things out and they write them down and we learn from it. So as long as you can understand it, that's all I care about. the fact that you may not have known how to do it, that's okay. There's tons of things I don't know how to prove off the top of my head. But I can follow these steps and I can explain it to you and you can understand it, that this equation doesn't just come from anywhere. Now really, the reason this thing works, the reason you flip the thing backwards is because there's a lot of symmetry in the arithmetic series. Because you're adding a constant number, if I flip the sequence of numbers around, then I'm kind of subtracting and going backwards the other way. Then when I add all the terms up, you get a ton of cancellations. That is why it works. And there's probably a million other dead ends you could go through to try to prove this that wouldn't be correct. But the bottom line is we know it's legal to write the series this direction. We know it's legal to get the same sum by flipping the terms around. When we add them, we know it's illegal to add the left, and we know it's illegal to add the right. And we get all those cancellations, which allows us to solve for the sum. That's all we care about, that we were able to prove that that is the sum. All right? So now what we want to do is we want to solve a couple of additional problems. Now that we have that basic idea of what's going on, we want to find the sum of these arithmetic series. So the first one is n is equal to 20. That means there's 20 terms. The first term is equal to 5, and the last term, which is 20, because it's 20 terms, is equal to 62. And I ask you, give me the sum of this. So all I've told you is that I have the first term and the last term, and how many terms I have. Now I could go into a calculator, and I could write these terms out, and I could just add them up, of course, but there's 20 of them. That's a lot of work. I want to just find the number. I want to figure out what it is. So you first start out by writing down the equation we just proved. The nth sum of an arithmetic series is n times t1 plus tn. First and last terms divide by 2. But I know in this case that I'm looking for the 20th partial sum, the first 20 terms here. And that means n is 20. And that means the first term is 5, the last term is 62, and I have to divide by 2 because on the bottom here, that's what the equation is, it's always divided by 2. So the 20th partial sum over here is going to be, when you take 20 and you add 5 plus 62 and you multiply by 20 and you divide by 2, you're going to get 670. And this is the final answer. Now, we could stop there because that's really all I asked you to do. But I think it's good for us to write out what the terms of this sequence would really look like. What are the terms of an arithmetic sequence, right? The terms we learned a long time ago. The nth term is equal to the first term plus n minus 1 times the common difference d. Okay? So I've only given you the first and the last term, and I've given you how many terms there are, but I haven't told you the spacing of the terms. What's the common difference between them? We didn't tell you that in the problem statement because you don't need it to find the sum. All you need to find the sum is the first, the last term, and the number of terms. That's it. But to write out the listing of terms, I need to know that spacing, the common difference. So let's put the final term in to be 62. Let's put the initial term in to be 5. We know it's 20 terms away, the first and the last term, so we'll put n is equal to 20 minus 1, and then we're going to find the spacing, the common difference. If we subtract this guy, we're going to get 57 is equal to, here we have 19 times d. So when you take 57 divided by 19, you get d is equal to 3. So the only way this arithmetic series works, if you start at 5 and 20 terms later you get 62, is if you space out by 3 units. That means the sequence will go, the series will go like this. 5 plus 3 more is 8, plus 3 more is 11, plus 3 more is 14, plus ... Eventually you're going to arrive at 62. And how many terms are there? If you write them all out, there's going to be 20 terms. Of course, you don't need to write the series out in order to find its sum. That's the whole point. You want to figure out what the sum is without doing all that work. I'm just kind of showing you so you kind of know and have in your mind exactly what you're doing. And so that you can write the series out if you ever need to. And the common difference here is 3 plus 3 plus 3 plus 3 and so on, landing on 62. All right? All right, one more, and then we'll call it a day for this one. What if I give you an arithmetic series with 40 terms, where the first term is negative 12, and the 40th term is equal to 183. This is a great example of using this equation, because I have 40 terms. If I could write the series out and add them up, but that's 40 additions. Certainly it's going to be easier to just apply the equation that we know. So first thing is you write down the equation. The nth partial sum is equal to n times the first term plus the last term divided by 2. Again, this is the average value of the terms times the number of terms. Now, this should not be 2. It should be t sub n, like this. Okay. So the 40th sum, the 40th partial sum, is going to be 40 times the first term, which is negative 12. The last term here is going to be t sub 40. Let me just double check myself. Yeah, t sub 40 is 183. And we're dividing by 2, like this. So the 40th partial sum is going to be 4 times what's in here. So 183 minus 12 times 4, you're going to get 6840 on the top, and you'll divide by 2. So the 40th partial sum, the sum of all those terms, is 3,420. Notice I didn't even have to know any of the terms in between. There's tons of terms in between negative 12 and 183. And by the way, don't get so worried if some of the terms are negative. So what? Some of the terms start to the left-hand side of 0. No big deal. But they're still spaced by an even number, or by a constant number. Let's go and, just because we did it for the last problem, let's do that same thing here. What is the equation to predict all the terms of this series? The nth term is the first term for arithmetic plus n minus 1 times the common difference. Now the last term we know is 183. The first term we know is negative 12. We want to figure out, or we know how many terms we have also, 40 terms here. So it's 40 for n minus 1, and we want to figure out what the common spacing is here. So when you take 183 and you add 12 to it, you're going to get 195, and over here you're going to get 39 times d. And if you take 195 and you divide by 39, you're going to get a d of 5. That means these terms are spaced out by 5. You're never going to be able to figure this kind of thing out just by staring at the numbers. You have to use the equation to predict all the terms in the sequence or in the series to figure that out. Now that you know the spacing is 5, you start at the first term, negative 12, and you add to it. The next term will be 5 from there. So let's do it like this. Negative 12. The next term is going to be negative 7 because that's 5 more. The next term is going to be negative 2 because that's 5 more than this. The next term after this will be positive 3 because that's 5 more after this. And then you're going to have plus ... and you're going to land on the last term, 183. So if you start here and add 5 and add 5 and add 5, add 5 all the way forward, do it 40 times, or 39 times really, then you're going to get to that 40th term, which is 183. This isn't really what I'm asking you to do in the problem. I just like you in the beginning not to just apply equations, without knowing what's going on. I want you to know that this is a sequence of numbers we're adding together. And you only need to know the first and the last term and the number of terms to tell me what the sum is. But if you're ever asked to write down the terms of the series, then you're going to need to be able to predict and figure out the spacing so that you can write those terms down. So in this lesson, we've done a lot of material. We already knew what a series was in math. We already knew that. But now we want to start to add up. We want to find the sum. So we introduced the concept of the partial sum. When you're adding up 2 terms, 3 terms, or 4 terms, the number underneath just tells you how many terms you're adding together. When you're adding up n terms, in other words, the equation to add up however many terms you want, is given by this, which we've discussed at great length. And then we did the proof of it, and then we solved some problems. And so what I want you to really pull out of this mostly is how to apply this to real problems, and also to know that the proof of where it comes from is not impossible to understand, all right? So what I want you to do now is solve these yourself. Go ahead and tackle that proof if you want to as well. And then follow me on to the next lesson. We'll solve some more problems with the arithmetic series.